So Matt, I went with something like I have an hour plus of tutorial, and then I thought we just leave room for discussions. I mean, yeah. Like the tutorial is really stuff to do. It's not me present. I mean, well, I'm going to present stuff, but there's as well stuff to be done by the participants. And then I can show you more stuff if we run out of time, or we can have a discussion. I thought.
Sure, yeah. You are the last, I think, to present for today together with Matt. Mm-hmm. So, yeah, take. I guess you can take your time.
Pardon me?
You can take your time.
Right. So, yeah, I want to. Okay. Do you hear some background coming from me, like voices of children?
Mm-hmm.
You do hear that?
A little bit, but it's not disturbing.
It's not disturbing?
No.
Okay. It looks like well, that's the time is now, right?
Yes. Are you ready?
Yep.
All right. So we will have a tutorial about probabilistic reasoning and pattern mining using OpenCog with Nil Geisweiller and Matthew.
Thanks for the introduction, EB. So the plan for this tutorial, first, we're going to have a little bit of preparation that we're going to do first because it involves downloading a Docker image. So better do that. And first, and during this time, I'll give a little presentation that are going to help participants to understand the notions that are being presented during the tutorial. And then I'll go on with the tutorial. And at the end of that, we can have a discussion, or I can show you more stuff. Yeah, it's kind of, it's open-ended. So the first thing you're going to do, if you want to actively participate, you're going to have to install Docker. And once you have installed Docker, you're going to pull do you see my mouse cursor? Do you see it?
Yes.
Yep. Okay. Right. So that's the instruction for Debian base and Arch base to install Docker. Well, if you have something else, I can't help you. And once you have installed Docker, that is the command line to download the image. If you happen to already have OpenCog installed on your system, I don't recommend to use it because actually in the last moment, as I was preparing the tutorial, I found a few bugs and I didn't have time to create proper fixes, and to merge them into the master branch. So I have works around, but they are on the Docker image, but they are not on the master branch. So yeah, so better if you just go with the Docker. So the command line to download Docker will be displayed at the bottom of each slide, so I can move on. Okay, so right. So the tutorial is going to be about OpenCog, as you know. We're going to focus primarily on reasoning, but I've got to give you a little bit of a recall about OpenCog. So it is a framework for AGI. The thing that the crux of it is that there is a central database, which is a hypergraph or metagraph, which is called the atom space. And on this atom space, we have a language called atomies that can be used to query this atom space. It can be used to rewrite the atom space as well. And so that's the core of it. And around this core, we have cognitive processes that we call mind agents that can operate on this atom space. So for instance, that can do some reasoning or some learning, maybe some data mining and so on. And as Ben mentioned in room 2, this is via this atom space that we can enable this cognitive synergy because they have this point of contact, which is the atoms in the atom space. So yeah, I mentioned atoms, so I'm going to have to explain what that is. So an atom is basically an element of this atom space, which can be a link or a node. And the particularity is that a link can be connected to a link as well. What else can I say? Yeah, so he's doing a bunch of stuff, like even natural language processing and stuff like that. But here we're going to focus on reasoning. Okay. So the primary logic used to reason on the atom space is called PLN, for probabilistic logic networks. It was invented by Ben and Matt and a few others. And it has a few qualities. First of all, it is based on probability theory. I mean, one might say probability theory plus because it incorporates, it goes beyond that, but the foundation is really on probability theory. It has, it incorporates representation and management of uncertainty. And the interesting thing about it is that this uncertainty is also grounded in a probability theory. I'll talk more about this. It is rather suitable for common sense reasoning, but can also be used for mathematical reasoning. And it can also be used to reason about resource management. And that's how we can do some form of meta reasoning, which I'll briefly talk about. So I'm going to go straight to the basic. So how do we represent probabilistic relationships in PLN? Well, we have this lane here, subset, and what subset AB says is that we have a certain probability of B knowing A. I mean, that's essentially what it is. So subset is the notion of subset in set theory. But the thing is that we have this probabilistic and even fuzzy probabilistic variation on it, which allows it to have a semantics, a probabilistic semantics. So what that means, so this what you see here is atomies. I mean, this is what we write in our atomic interpreter, or whichever variation we use, to enter this knowledge into the atom space. This thing here is the truth value. STV stands for simple truth value. Okay, as I said, a subset of AB represents the probability of B knowing A. S is the strength, which is the probability itself. And C is the confidence, with some formula, which, I mean, doesn't really matter what is the formula. It only matters that it's a monotonic mapping between the number of observations and the range 0, 1. Whoop. Let me. Okay. All right. Any questions so far? If I don't hear anything within the next 5 seconds, I'll move on.
So I think, Nil, you mentioned the confidence, and you can also map confidence to the evidence, the gathered. So there's a back and forth one can do.
Yeah. So that's exactly what I was saying. So the size of A would be basically the number of observations. And so, as you can see, when the number of observations is growing, this thing is gonna tend to 1, right? And I mean, okay, I'm gonna move on.
Yeah, that was all I just want to just mention that there was this correspondence.
I mean, yeah. So that's exactly what I wanted to present next. Is that the interesting thing about a truth value is that, well, I mean, okay, STV stands for simple truth value, but why simple? Well, as you guess, the reason is because there can be less simple or complex truth value. And why is because a truth value underneath is actually a second order distribution. So as I was saying, that uncertainty is grounded in probability theory. It's really this. It's that when we talk about a truth value, we are talking about a probability of a probability. And so here are some examples of distributions, of these second order distributions. The first two would be the case where we know absolutely nothing. So there is something, there is a pattern, whatever. There is an event and we know absolutely nothing about this event, and it could have a certain probability. And if we don't know anything and we take a Bayesian prior, then this probability would be completely flat. If we take a Jeffers prior, the probability would be slightly concave. And as measured as we accumulate observations, we're going to narrow down this distribution to something well, more precise. And if we go to infinity, we get a Dirac distribution. Okay, I mean, it's all well and simple, but this actually is only true if your second order distribution is a beta distribution. And that works well, but in some cases you need to go beyond that. And so when you need to go beyond that, well, you need to resort to more complex truth values. So as you've seen, a simple truth value is two numbers, is characterized by two numbers, a strength and a confidence. And a beta distribution is characterized by two numbers, alpha and beta. And so that works. But as soon as you start to do some reasoning, or you start to aggregate knowledge coming from different sources, then the beta distribution breaks down a little bit. But overall, that work well when you just want to account for observations. Yeah, direct observations. So where are we? Okay, so any questions so far? Okay. So here's an example, for instance. Here we have this simple knowledge base. Okay, we have probability of B knowing A is this, probability of C knowing B is this. And we know that A is true with a certain probability and confidence. And we can use these rules. So here it's a deduction rule. So knowing, well, sometimes I'm going to say, so the thing is that there's actually, I mean, this notion of subset is actually isomorphic to a notion of implication. So when it's convenient, when it flows well, I'll say implication. And so we could read this rule as if X implies Y and Y implies Z, then X implies Z. And of course, it's true to some degrees, and that's going to depend on the truth value here, and well, this one is going to be calculated by the rule. So here we have the modus ponens, which has been again probabilitized. If we have if X implies Y and we have X, then we have Y to some degree. Okay, so what can we do when we have that? Well, we can basically plug together these rules to construct inference trees or inference graphs to prove things. So given certain some axioms or some knowledge base, and given these rules, we can start to ask questions, or we can simply run the system in a forward manner and just ask it to infer all possible theorems. Oh, sorry, I have to. Okay, so that's what I was saying. So here's a simple example of an inference tree. So given the knowledge base that we have here, is it this? Yeah. Given the knowledge base that we have here, how can we infer the truth value of C? Well, we can construct this inference tree that first construct the implication of A and C with a certain truth value. And given that we have A with a certain truth value, then we are going to be able to infer C. Okay, so that's a very simple example. But basically, I mean, PLN, it might look intimidating when we look at it the first time, but actually it's rather simple, because it is really constructed on this simple probabilistic / uncertainty rules. I mean, it's everything else is just built on top of that. So I mean, it's more subtle than that. For instance, we have, when we start to get into universal instantiation, I mean, we do need to quantifiers and things like that. We do need to invoke a third order distribution, but apart from these subtleties, it's really just based on these simple things. We have also intentional reasoning, which is also based on that. Intentional reasoning is extensional reasoning, classical probabilistic reasoning, but instead of using the sample space, instead of using members, observations, we are using a sample space of patterns. And everything else is, we also have the notion of contextual reasoning, but all this can be mapped into the basic form of reasoning as well, and so temporal and spatial. Okay. All right. So, of course, reasoning is nice, but the problem is that it's generally inefficient. And in order to have efficient reasoning, so basically PLN is implemented on top of what we call the unified rule engine. And this unified rule engine is able to accept control rules to guide the inferences. Now, the interesting thing is that these control rules are atomist code. So basically, because of that, they can be learned, they can be reasoned, and this enables some form of meta reasoning. So the most simple case we have for control rule is a context-free control rule. So basically, it's equivalent of having a weight on the rule. So an example would be, for instance, okay, let's choose deduction 90% of the time and modus ponens 10% of the time. And it can help, but it's not going to go very far if the inference starts to be too complicated. Something that can be really powerful is a context-sensitive control rule, where we relate the rule to, well, the fact that we are going to have a successful inference, but also the context. And so this allows to dynamically adjust the weights of how we're going to choose the rules to efficiently guide the inference. What else do I have to say about this? Did I forget something?
I think this is good. I mean, we can go into further depth on that later on, yep. But
okay,
I think at this level, this is good.
Okay. All right. So, okay. So now we have the pattern miner that comes in Y. Well, there are different reasons, but first of all, the pattern miner is one way. Well, I mean, why do we need to mine patterns in the first place? So one reason would be to just learn context-sensitive control rules. For instance, we can learn a bunch of inferences. I mean, we can just run a bunch of inferences, and then we keep a trace of these. These traces, they live in the atom space, and so we can mine these traces, and we can start to build this sort of context-sensitive control rules. And to relate the context to the rule and to the fact that it's a successful inference, the pattern miner can help. And the thing is that the other related aspect is that the pattern miner itself is actually implemented on the rule engine. So it is a form of reasoning. It's not completely, I mean, it's not a fully transparent form of reasoning, although it could be in practice. But yet the interesting thing is that because it's a form of reasoning, the pattern miner itself can benefit from learning inference control rules. And so this is really an example of fully recursive meta reasoning, where basically the only limit is as long, I mean, if whatever control rule you learn is abstract enough, if it's abstract enough to apply to your problem, well, it's great. But if it's even if it's so abstract that it can even apply to your problem of minding inference control rules, well, then that's great. Because in one shot, you just, I mean, you can go to several levels. Of course, I mean, there's a catch, which is that the more a control rule is abstract, the less predictive power it's going to have. I mean, that's typically the case. I mean, the only way to have a good predictive power is to basically consider restricted domains. As long as if you start to consider everything, the whole universe, then it becomes very difficult to have strong predictive power. But nevertheless, okay, so let's go back to the pattern miner. And so here's a simple example. So we have these relationships in the atom space. And well, we can see visually that there is some pattern. And we can run the pattern miner to discover this. So for instance, we have, so okay, let me explain. Patterns are called, in fact, frequent patterns because they have to be frequent enough in order to be accepted. And so if we set the minimum frequency, I mean, the minimum count to 3, then we do find that this particular pattern, well, A is a subset of B or a subset of C or a subset of D. Well, it's a subset of something. Okay, that's a pattern. We have another pattern, which B is a subset of E, and C is a subset of E, and D is a subset of E. Well, something is the subset of E. Okay, that's another pattern. And we have this pattern as well that combines the two, where A is a subset of something, and this something is the subset of E. Okay, so these are the kind of patterns that we can discover with a pattern miner. All right, so, okay, so that would be like the most generic, greedy pattern mining algorithm, which I don't really need to explain in detail. It's the main thing is you start with the most abstract pattern, and you see the if it's frequent enough. Well, if your database is big enough, it should be frequent enough. It's because it captures all the instances of the database. And from this top pattern, you start to specialize, and you check if the specialization is frequent enough. And if it's frequent enough, you keep it. If it's not frequent enough, then you discard it, and you don't need to explore any subsequent specialization of it because, well, if that one is not frequent enough, any specialization are going to be less frequent. And so that allows you to prune the search space rather effectively, depending on the minimum support that you consider, the minimum count. Okay, so basically I said that the pattern miner was actually implemented as a form of reasoning. So how do we do that? Well, we basically take this this simple property, which is called the a priori property, which says that if a pattern is frequent enough, then any abstraction of this pattern, let me read that. I don't want to get confused. So Q is the specialization of P. So P is the abstraction. And right. So the premise is, if some pattern is frequent enough, then any abstraction of this pattern is going to be frequent enough. All right. And so we take this rule and we start with the top pattern, and then we run this rule backward and we generate the specialization. And if the specialization is frequent enough, then we can keep going backward. And if it's not frequent enough, then we stop. All right. So, right, but so frequency, I mean, pruning by frequency is nice and efficient, but the problem though is that depending on the cases, you might still have a lot of patterns, and they might also you might just not discover patterns that are frequent enough that seem to be useful. And when you lower the threshold of frequency, then you get tons of patterns and you don't know how to sort out what's interesting, what's not interesting. And so on top of that, we have a notion of surprisingness, a measure of surprisingness, which is also implemented as a form of reasoning. Basically, I mean, this notion of surprisingness really could be anything you want, I guess, but here in our case, we have used the distance between the truth values of the patterns that we are mining, and it would be so the difference between the empirical truth value and the estimate. So the estimate is basically how would you expect that this pattern would be doing under your assumption of the world. And the empirical is how it's actually doing. And so if it's too different, well, then it's surprising. So how do we represent that as a form of reasoning? So let me check the time to see if I'm not drifting too much, because you know when you give it. Hey, I'm realizing something. You are, because this. Wait, that's very confusing. I mean, I suppose you are seeing my slides because you would have told me otherwise.
Yeah,
because because Zoom is showing that on another screen. Okay, I was slightly worried that Zoom was playing a trick on me, but that doesn't seem to be the case. So, okay. No, very odd. Okay, anyways. Yeah, okay. Okay, I've been doing that for half an hour, am I correct?
Mm-hmm.
All right. Okay. So I don't know how much I should detail of that. But I can show quickly. So we have the surprisingness here, which is what we want to assess. And here we have this notion of distance. It's a Jensen-Shannon distance, but really it could be something else. Here we have the estimate. Here we have the empirical. And the interesting thing about this, when you frame that into reasoning, is that in order to get the estimate, to infer the estimate, well, then it becomes an inference problem. So there's an infinite way. There are infinite ways to estimate that. To estimate an estimate, it depends on what you know. It depends on your assumption about the world, et cetera, et cetera. And by doing that, basically, it opens the door to, for instance, a more dynamic surprisingness measure. That is, you saw something first, it wasn't looking very surprising, but then, well, you have updated your model of the world, and then you can take this into account, and the next time you see something that relates to it, it will be less surprising. So it's a very powerful way to measure surprisingness. Okay, well, that's, I mean, it's a work in progress. We are scratching the surface at this point, but it is certainly promising. Okay, so we can move on to the tutorial itself.
Nil, I think this would be a good time. There's a couple questions, or
right,
at least that came up on the chat.
Okay, great.
So I think Mike Miller has a really good question about the knowledge base and rule set, whether it's synthesized by another programmer or is it's hand constructed. I can answer, or I'll let you answer either way.
Yeah, I mean, yeah, I mean, you can go ahead if you want, and maybe I can complement.
Well, so I think there's two questions there, right? There's the knowledge base, which is essentially, if you think about it, it comes from experience. As you gain more knowledge, so the knowledge base is not manually constructed, but the rule set, it is probability theory at an underlying level. So at this point, at least, and that's why I kind of really wanted to address it. Like the deduction rule is based on the standard probabilistic deduction rule at some level. What's different is its reasoning under an uncertain world. But I think the interesting part is, how do patterns pay into construction of rule set? Is that something when we talk about meta learning?
Yeah. So I didn't mention that, but the rules are actually described in atomies. So I mean, as of today, actually, they are not 100% described in atomies, but we can nearly do that at this point. And so basically, yes, they are hand coded initially, but then it's possible to enable the system to learn them. And in fact, it will probably be really desirable. I mean, when you think of deduction, for instance, yeah, deduction is, I mean, works well under some assumptions of independence and so on. But if you start to, if you want to go beyond that, well, the deduction rule is gonna, I mean, it's gonna grow in complexity, or it's gonna be more open-ended, and it's gonna be needed to be, you're gonna need to plug more stuff into it. It's gonna have more premises and so on. And there's a trade-off which is just not easy to get by hand at this point. So having the possibility to learn them is obviously a good thing.
Right. So in terms of the actual theory, I mean, the base layer is based upon human knowledge, right? The probability theory.
Right.
But then we're building different pieces, and I think atop that, and that's where the meta learning comes in, the surprisingness for learning, discovering new patterns. And another thing that I think and maybe I don't know, because I didn't go through the talk with you beforehand, but the inference complexity, which you touched on in terms of context. I think at some point, I don't know if you're going to be talking about the cognitive synergy aspects and how that would play in for reasoning as well at some point.
Yeah, so
Maybe
I
towards
mean,
the end.
yeah, yes, I'm done with my presentation for now, but what I can say about this is that, I mean, there are certainly, I mean, each learning algorithm has its own biases, and obviously some are just more amenable to get off the ground, basically. I mean, they might not be very general, but they're general enough to learn some useful patterns about the world, or about I mean, the inner world, the control of the system itself. So it's a nice thing to allow these more specialized, well, not necessarily more specialized, but these learning algorithms with their own strengths and weaknesses, to allow them to basically give what they have to give before there is a more full-on, just completely self-rewriting, completely, I mean, self-aware, self-rewriting, etc. system that would then, I guess, eventually don't necessarily need these algorithms anymore, or is going to create its own algorithms. Yeah, I don't know if
okay.
Yeah.
I don't see any other questions on the chat. Any questions from anyone else?
I have one question. Do you hear me?
Yep.
It's about the possibility that, as you said, there are some basic, maybe some kind of a building blocks, logical, probabilistic logical building blocks within the system, and system starts to work on some kind of application, for some kind of application. And is it possible that along the way, these building blocks, these basic building blocks, enable some kind of embedding of this very specialized, some kind of new type of already specialized logic for this application, some sort of embedding of something which is not programmed or built in the first place?
I'm sorry, there's a word I didn't understand. Did you say embedding?
Yes, embedded application-specific logic for, yeah.
Yeah, so I think ultimately it has to do that, because I mean, like even the control rules, I mean, okay, it's nice, you have control rules, you have a lot of knowledge, and you get better at choosing the next rule to apply in your inference. But the thing is that you're going to accumulate rules over time, and then at some point, even choosing a rule becomes extremely costly. So then, okay, well, we have ECAN, we have attention allocation, but at some point, this attention allocation also is going to blow off. And so at some point, you need, I mean, there's just no way around that. You need to turn this machine into some, I mean, it needs to be able to turn some of its parts into just, more automatic, just algorithms, just code that is, we know that it's going to do well, and so we can just turn all these complex interactions into some simple code that is just going to do well in this context. And I mean, it's very much like our autonomous behaviors, the way, I mean, we walk without thinking about it, etc. But I don't know if that was your question, but
yeah, that helped. That cleared a lot. So there is a possibility that something like this basically grows on itself without autonomously in some certain way.
That would definitely be the goal. I like Nil's example towards the end there. Yeah, we as humans, we learn to walk and run and jump. But then occasionally you trip. And every time you come across one of those examples of tripping, say, you learn, you get better, you modify, and hopefully it begins the takeoff, right?
Yeah, so
it never becomes totally automatic. It becomes totally automatic until it doesn't.
Yeah, so I mean, the way I see it is that there is some sort of Uber planner that is able to notice that some parts can be automatized, and so all these can be orchestrated, I believe, via reasoning. Yeah, I mean, I think the Gödel machine is a good conceptual framework to think about this. Yeah, I mean, it's we're not there yet, but I think it's the direction that it should go.
Thanks, thank you.
Or at least it could go. So okay, so now I'm gonna unshare the screen to share another screen. So I'm gonna have to find really odd. Okay. Okay, I think I got it. So I need to have Zoom. Oh, okay, interesting. Okay, so now you should see a terminal with some Docker command. Right, okay. So assuming that you have downloaded the image, now we're gonna run the image. So like, should I press enter right away, or do you want me to, maybe I should let a little bit of time for others to type the command? I'll give 1 minute maybe. How are we about doing this call? Is there anybody trying to follow along, or?
Yes, we have someone who's very enthusiastic on YouTube called Andre, who is following along step by step, and he cannot wait for your next instructions.
Okay. All right, great. Oh yeah, excellent. Okay, so I guess I'll type enter, and yeah, if someone wants to go back to it, I guess I'll go back to it. Okay, so now I'm inside the Docker image. So I've installed Emacs, Vim, BioBoo, less nano. I think that's about it. Screen as well. So I mean, I'm entering Emacs, but anyone can stay in the terminal. It's fine too. But the thing is that having Emacs or BioBrew or screen just allows to see a README as well as entering commands so on the same screen. So that's why I'm doing that. Okay, I'm gonna enter in the current directory. We've got this file, AGI 20 PLN tutorial, follow along. It's a markup file. So, okay, I'm entering this file. And I'm gonna have a shell in the other window. All right. Right. So if you want to use, I mean, if you are familiar with one of these tools, well, it might make the tutorial easier. Otherwise, you can just stay in Bash. Okay. So the first thing we're going to do is enter Guile, the Guile interpreter. Okay. And then we're going to load OpenCog, and we're going to load Atomy. So I'm going to type everything so that this is going to ensure that I'm not going too fast. All right. Okay, it's going to take maybe 1 minute because the first time it has to compile and it's a fresh image. Okay. Okay. Now I can't even show myself. So. Okay. All right. So we're gonna enter all that in the Elm space. So concept, it essentially means a set. So it's something that can have elements. So here we're gonna create the concept A, and we're gonna add some truth value to it. So here it means 0, 1. It has a strength of 0, 1, meaning the probability estimate of this concept being a representation of the universe is 0, 1 with a confidence 0.6. Okay, so now let's enter B. Let's enter C. So we're not going to provide a truth value to C, and that means that it has a default truth value. So the default truth value is actually complete ignorance. So if I enter this, it's going to be the same. So as you can see, the confidence here is 0. Meaning, I mean, the value here, it could be anything. It doesn't matter. It's just it's a flat distribution. Okay, here we have a subset. So this means that the probability of B implies A is 0.8. Okay, and now we're going to do the same with, oh, well, maybe I made something wrong here. Anyway. Yeah, pardon me, it's A implies B. I think I. All right. Okay, so now we can see what we have so far in the atom space. All right, Cog PRT atom space. Okay, as you can see, it didn't bother to redisplay ABC because there are already subgraphs of the subset links. Okay, so now that we have this, we're going to query this knowledge base. So let's first add some shortcuts. So define is just a well. So basically, so we are inside Guy. So it's a dialect of Lisp, and Lisp is basically the functions are in lowercase, while the atomies functions are in a camel case. That's a good way to make the distinction between just Lisp and atomies. All right. So these are variables. So they are atomies variables. And here we're going to define a shortcut for a type. So again, it's so this is atomy. So it means that it's the type concept in atomies. All right. Okay, and now we're going to write some queries. So let's start with something very simple. We want to query all concepts. So we're going to use get. So first we're going to use cog execute, which is basically the scheme primitive to run the atomies interpreter. Then we're going to use get to basically query the atom space. Here we have to construct type variable to type a variable. Okay. Then we use present, which is going to check whether whatever it comes across is going to be present. Well, the reason we have this thing is because we can have other kind of predicates. So that's why it's not how to say. That's why it's useful. But actually, what's going on here? Oh. All right, some little typo. All right. Whoop. What did I do? Oh, I forgot the get. Okay. Well, it's good that I make so many mistakes. That way, if someone else make mistakes, it will not get lost. However, I'm also going very slowly. So let's try that. Okay, it works. Okay. So yeah, I see that it's already, Jesus. Time flies. So okay, I'm not going to type everything. If someone misses, it's okay. I mean, it's basically at this point, it's just for the show, for this part at least. So here, this query, what this query does is instead of fetching the concept, it's going to fetch all the elements of subsets. And if I want to fetch the subsets themselves, then I can use that. Okay, I'm gonna type this one because it's important. Here I'm using bind, which is like get, but it's also going to produce something, not just fetch something, but also produce whatever you give it in third argument. So here I'm going to have multiple variables, so I'm using variable list. And I'm going to put again my type variable x. So x is a concept. Okay. Y is also a concept. Okay, so that's for my variable declaration. Now I'm going to use percent again, so I want x, y, and a third argument. This is what's going to be produced. Of course, here everything that's going to be produced is already in the atom space. Okay, so we have all subsets. But in the next one, we're going to produce something new. So, okay, I'm not going to type this one because, I mean, there's nothing new in it. But the result's going to be new. That is, I mean, it's basically a one-step transitive closure. So if we have x is a subset of y and y is a subset of x, then we can infer that x is a subset of z. So okay, let's do it. So it's able to generate that. So now if I well, okay, let's do cog print atom space. We're going to see a lot of stuff now because the thing is that all these queries now they are in the atom space. Okay, if we don't want them in the atom space, we can actually create another atom space and put them there in the first place. But that's not what we've done. Here if we look for it, we should be able to find, yes, it is here. A is a subset of C. All right, the newly inferred knowledge. However, this thing is just, it's completely crisp. It didn't use some truth value on the subsets, and it didn't produce a truth value. And what PLN is going to do is basically that, but at the step where we have to rewrite the term, it's going to invoke a formula, and this formula is going to calculate the truth value. All right, so we're going to move to PLN, which is going to do just that. So let's load PLN. Okay. All right. So now we are going to load an empty rule base. I mean, because there are different layers of PLN, and we're going to start from empty. And we're going to add just the rules that we need, which are deduction, and modus ponens. Okay. PLN actually lives in another atom space that can be printed with PLN PRT atom space. Okay, so there's a lot of stuff here. That's because it has loaded all the available rules, or most of them. However, we have only attached 2 rules, and they can be displayed with the PLN rules command. We can also show their weights with PLN weighted rules. As you can notice here, the weight is not a single value, it's a truth value. That's very important because it allows not just to give a priority to rules, but also to balance exploitation and exploration. So here, everything is flat. So basically, what it means is that we have no idea what is better than the other. Okay. If we had some idea, then we could say, oh well, I have some little ideas that modus ponens is maybe it's a little bit better than a deduction rule. But because we have some low confidence, there's going to be a lot of exploration still going on with that. And if we want less exploration, well, then we increase the confidence and so on. All right, so now let's try to use these rules. Okay, we're going to use the same thing we had before, but let's just remove a lot of junk in the atom state that we have accumulated. So that's just what we had before. If someone cannot copy paste and wants to follow along, this someone's going to have to retype everything, and I apologize for that. I don't know if I have to wait this someone or if I should move on. Let me just wait a little bit. So this is this thing. While I'm waiting, any question?
I think somebody on the YouTube chat was having a little bit of issues working with Emacs. So whether you could quickly just like show how to do it differently for them, perhaps.
Well, yeah, I mean, for someone who's not used to Emacs is a little bit of a problem. Yeah, I mean, I would, so, okay, if someone is starting from scratch, like someone has tried Emacs and wasn't able to use it. Okay. Before I say that, just let me, I mean, just to give us a chance to Emacs. In order to change the window, it's Control XO. Okay, Control XO. What else should I say? In order to bring the shell, it would be Alt X, and then you can type shell. Okay. In order to split the screen in two, you do Control X and 3. Okay. And if you want to remove the splitting, you do Control X and 0, sorry. Control X and 0. Here I'm going to split again. Control XO to move to this screen, to this window buffer, we say in Emacs. Control X to come back. Control XO to come back, I want to say. I'm going to select the shell with Control X B, and I type shell, and I'm there. But if someone wants to start from scratch at this point, it's still possible. All that this someone has to do is re-import everything, OpenCog. I think actually only that's going to be necessary. I think that's going to be enough. Use modules, OpenCog, OpenCog PLN, then load. So let me just show as much as I can. Right, so here I'm showing everything. All right, so import OpenCog and PLN, load the anti-rule base, add these two rules. Well, this is not necessary, and then can bring the knowledge base, which that's all of it, right? Okay. By now, do you think I should move on, or I should, or?
Yeah, I think if there are no other questions, then we can just move on.
Okay, great. Okay, so before I run PLN, I'm going to set some parameter. So this is going to allow to, so the name of the parameter is complexity penalty. I set it to 10, and what that means is that PLN is going to focus on simpler inference trees first. I do that because otherwise I might run into the risk of having PLN just evolve bigger and bigger inference trees in a runaway fashion, and it might miss the this simple inference that we want here. Okay, so interestingly enough, the parameter actually exists inside the atom space, the PLN atom space. And so now, okay, let me type it. So PLN BC stands for backward chainer. What that means is that we're going to start from a theorem, and we're going to go backward. We're going to apply the rules backward until we reach the knowledge base. So, okay, let's try. Okay, it seems to work. So it has applied. Here is just one rule. It's a deduction. Okay, to see what's going on behind the surface, we can enable the logger. So we're going to set the level of the rule engine to debug, and we're going to have it display things right in front of our eyes. Okay, and now we're going to rerun the same thing. So before that, I'm going to have to reset the truth value of C, the target. Well, sorry, just a second. Oui, là je peux pas, là, je suis... Ben oui, mais attends. Oui. Ok. What? Ben si, il y a une caméra. Mais elle te voit pas, t'inquiète pas. Alors. Okay, so where was I? Yeah. So okay, we are resetting the truth value of C. Okay, and we're going to rerun. Oh, what is that? Yeah, so we were here, right? So we're going to rerun the backward chainer on C. And it's going to display a lot of stuff. So we're going to limit the number of iterations to 10. And okay. So obviously I can't explain much of what's going on here, but there's something I'd like to show you. And these are the inference trees. So this one is actually already more complicated than we need. The one that gave us the answer, well, it is this one. Wait, I've lost track of. Yeah, no, actually, it is more complicated than that. It's going to be this one. Yeah, and you can see that the results here. Well, that's what we were looking for. Oh, actually, well, okay, something going on here. Sorry, a little bit of disturbance. Okay, I could lock myself again, so should be okay. All right. Okay, well, there's a little bit of there's something there's a little bit of fuckery here. I don't know what that is. I guess that there's another inference tree that is producing another value. All right, so that's where, I mean, dealing with uncertainty is very tricky, because like you obviously have many more paths to reach the same conclusion. Yeah, so this is something that is often a well, rather tricky aspect to deal with. Okay, but let's move on for now. So okay, now we're gonna so okay, we have 15 minutes left. Do you want me to keep going with PLN, or do you want me to move on to the pattern miner? Maybe I can show this thing, but very quickly. Right. So I'm just gonna.
One person says pattern miner.
Right. Okay. Okay. So I'm not gonna type that. So I mean, it is just to show that we can also do reasoning based on evidence, based on direct evidence. I mean, so it's kind of a idiotic example about the probability of growing a beard during a pandemic based on a very small sample of people. The interesting thing here is that we have these kind of rules that, this one is called subset direct introduction, and direct means that it's basically direct evidence. So we're going to look at, so the direct evidence are these members of, okay, this instance of individual happened to go through a pandemic, okay? This instance of individual happened to have a beard, okay? And so based on that, is going to be able to estimate the truth value of such a, just a second, sorry. Okay. Okay. And so, okay, we're gonna disable the log because it's gonna be overwhelming. And so now we can based on direct evidence, infer the probability of growing a beard during a pandemic. Okay. So, well, based on the evidence, it is the correct probability. Okay, but what about, for instance, growing a beard during a pandemic? Why being a man? Okay, it should be much larger. Okay, so let's run PLN over that. So it's not able to infer anything, and the reason is because it doesn't know how to deal with that. I mean, there are no rules to deal with this conjunction of man and pandemic. So for that, we're going to need to okay. And for that, we're going to need to add some more rules. Okay. And then we can, so okay, let me just go over these rules rapidly. So here we have this rule, conjunction direct introduction, that allows us to basically, given two concepts where we have direct knowledge about them, how to deal about the conjunction of that. Here we have something that allows to infer, to evaluate the truth value of a concept, well, given direct evidence, and here we need this thing because, well, I mean, I was too quick to show that, but basically there are some things that we don't know directly, so and so there's a little bit of inference to be done in order to extract this direct knowledge. And now that we have this, oh, doesn't work. I mean, maybe we didn't put enough iterations, so let's just, I'm going to put 1,000 to be really sure. It's taking a little bit of time, but should be over soon. Right, and so it found the correct answer. Because, well, based on the available evidence, well, the probability of growing a beard for a man being in a pandemic is 1. Right, okay. So let's move on to the pattern miner. So let's clear the atom space. Yeah, I've got like 10 minutes left, so I guess I'm just gonna copy paste until the end. All right, so this is basically what was in the presentation. So A is a subset of B, which is a subset of C, which is a subset of D, etc. So just want to see if we can find what we're supposed to find. What's wrong here? Oh yeah, I forgot this step. I didn't load the pattern miner. Okay, let's try again. Okay, so it has found a bunch of stuff. Yeah, and the most surprising one is the one that we're looking for. So it's basically A is a subset of something, and this something is the subset of E. I mean, so it's basically here. Okay, that's a little bit more complicated than what was in the presentation, and that's because here we have actually the measure of surprisingness of that pattern, which is going to be this value here. And it's a single value. That's why the confidence is at 1. And you can see that this pattern is read by a lambda link. A lambda link is I mean, it means the same as in lambda calculus, but basically it is a function that if I give this function to atomies, to the pattern matcher, it's going to be turned into a query. So basically, I can turn this pattern into a query, which can be very convenient to understand. Well, why this pattern is surprising? What are the data behind this pattern? Okay. Okay. And here we have another example. So let me clear the atom space again. So it's also a toy example, but I mean, I can only present toy examples because otherwise computation would go would take too long. I mean, we have experimented the pattern miner on some interesting data sets, sumo ontology, bioatom space, biology data set, which include, millions of atoms. And of course, it works, but I mean, it takes a long time. So for a live tutorial like that, I can only show a moderately simple data set. So KB, here it is. Well, it's a goofy data set about people drinking soda and stuff like that. And the pattern that we want to find is it's going to be this one if it works. Let's see. And it doesn't. Okay, what's wrong? Why did it work? Yeah, I tested everything in this tutorial except this last one. So
I think it's an extra bracket at the end of that line.
That shouldn't be the reason. Let's see, but I mean, invalid handle. That's odd. I think it has to do with that, but it worked before.
I was able to execute just by deleting the last brackets.
What did you do?
Just deleted the ending bracket. That was not necessary. That one is not necessary, and just copy paste that. It should, I guess, it should work. It works here.
Yeah, I might have included something else as well. Maybe oh, that's odd. I did a clean. I mean clear. And maybe you didn't do that. You know, I did that clear. And I wonder if maybe there was something useful,
right?
And it was cleared or something like that.
Maybe.
Anyways, I mean, I don't know if there's a point debugging that right now. I think it's already a pretty good overview of what can be done. and we have only 2 minutes left. So it's better to use that as maybe questions or
I think, oh yes, okay. For some reason I thought it went another half hour, but you're right.
oh yeah, maybe. Oh, I think you're right.
No, but either way, I mean, there's nothing after this, so if people have questions, we can take them until the end, so. But it does end at 2 Eastern time.
Yeah. I mean, I had. I mean, well, anyways, I mean, I think it's. I mean, it can be the end of the tutorial, and yeah. Any question or.
Predrag, I probably strong would say, says extra bracket, delete ending bracket.
Yeah, that was regarding the last statement, but it's
the last statement. Okay.
Yeah, I mean, it works here. But now that you mentioned my name, I have one question regarding this lambda link. What kind of, because I'm very new to COG, what kind of functional language expressions or constructs you can basically have within the atom space, and can you somehow describe types?
So yeah. So we have everything, but I mean, I want to say almost the most essential. We don't have currying. We could have it. I mean, it's just we just need to introduce this link, this operator, and we would have currying, and then we would have, I think, everything. I mean, well, the type system is not the most elegant one you can get, but I mean, we could turn it into an elegant type system. Other than that, I think we have. It should be basically lambda calculus plus or something.
And if you, I mean, can you somehow compare it to some existing popular functional programming language? Is that does that make sense at all? I mean,
well, so okay, yeah, I think I oversaw something. We don't have either, for instance. I mean, the notion of purity is very sketchy, and it's not basically. We don't have monad or things like that. Nothing is guaranteed to be pure. So I think we need to have a way to enforce purity. I think it can be done in the type system, or maybe in the hierarchy of atom types. We need to add currying. And if we have these, I think we have, I mean, it's not going to be Haskell because the syntax is rather different, but beyond that, I mean, let's say it's going to be, it could be Haskell with a bad syntax or something like that. And so with a limited type system.
I see. That's useful, because now people who have this kind of background can can get into the
yeah. I mean,
it's easier.
I think these functional additions are extremely useful. I mean, it's not just. I mean, the purity is extremely useful when you want to memorize anything. Memorize reasoning, memorize computing, etc. So I think it's very important, and I think it's gonna get I mean, it's going to be added whenever the need is going to be pressing enough. It's going to be added, I suppose. I mean, either it's going to be in this version of the atom space or in the next one. But
so when you say memorization, is that just for practical scalability purposes, or sometimes that can be something which has some theoretical consequences, using memorization or not using memorization?
I mean, well, I mean, if practice is taken in a broad sense, I mean, if you know, efficiency is, I think it's only for efficiency. I don't see another. I mean, I think I see what you mean, in the sense that, right, if you reason about a part of your environment that is just completely static, you're going to be able to enable well, some inferences that you won't be able to do if it's dynamic. So I can see that.
Okay, right.
Добре, чакайте.
Memoization, I mean, that affects what size patterns you can actually learn within a certain amount of time. So, I mean, in a sense, that's scalability, but I mean, it affects what the learning can do. So, I mean, in that sense, it's not like the system will come to the same conclusion, but just faster. I think it will find different things in a real context.
Right. I understand what you mean. So yeah, it's definitely, it has some practical consequences. Yeah.
I mean, it's changing the distribution. Yeah, it's changing the distribution of the learnabilities of different possible patterns, I think.
Right. Yeah, because probably the most of the applications in the real world will be complex enough, so this could impact in some very important ways the operation of the system. I see.
Yeah, because the patterns where memoization can help a lot ultimately they're gonna more often be parts of larger patterns. So it should affect the distribution of which patterns are more easily learnable by the system within a certain amount of time. I mean, if we tried to cash that out in a mathematical way, which we haven't done.
No, but I mean, the memorization is important, interesting to me, because I saw some of those prologue systems where they, I mean, I don't know if tabling is something related to this, but it has some consequences, but I'm not so sure where this is, but it seems similar in some ways. Because there are some things here, from what I can see in this scheme code and also in background system, that reminds me about the prologue systems. Of course, there are some prologue systems.
Yeah, there's some similarity there. I mean, of course, I'd say, as Linus Vepstas has pointed out, there's a bunch of similarities between what we do in OpenCog with pattern matching and probably data log more than straightforward
pure version.
It's a bit, it's a bit like probabilistic data log in a way, except I mean the underlying search algorithms are not the same, but still the implications of memoization for what is more easily provable or learnable may be similar to what you're thinking of. Yeah.
Thanks, guys. Maybe somebody else has some other question. I don't want to bug everybody.
Oh, you're not bugging us. You can say whatever you want, of course.
Okay, sure. Great. I mean, it's excellent that this is virtual. Everybody can participate.
That's true. That's true. It's open for all. Let's see. Any questions? Check the chats.
Yeah, this
Go ahead. Okay, there are no further questions anymore. Ben, would you like to give a last word, perhaps?
this is not a question, but it's a comment on something that I didn't hear all of Nil's tutorial, but I think one additional point that's interesting to reflect on is the interoperation between pattern mining, which Nil has been working on and showing off, and then probabilistic inference on the one hand, and evolutionary learning on the other hand, both of which also exist in OpenCog. Because I mean, as Nil has already done some examples of, sometimes the best way to do pattern mining is to hybridize it with inference, which is sort of a unique point you get from doing pattern mining in something like OpenCog. So like if you were I mean, as a simple example, suppose you were mining an Adam space full of people, data about people and their jobs, and you wanted to learn, how many people who hate their jobs are also depressed, right? So, I mean, one thing you can do is just have the pattern miner scan through the Adam space, and for each person it visits, check how many people hate their job and are depressed according to the knowledge explicitly in the Adam space. Another thing you could do is go through and for each person in the Adam space, do a little bit of reasoning to say, well, do I have a reason to believe they hate their job? Do I have a reason to believe they're depressed? And maybe for some person you find information that they they're saying they hate all the people at their job, or you find data about their happiness level throughout the day. You find they were happier at home than on the job or something. So you have indirect evidence that they hate their job. And so then one can use the pattern miner just to look for patterns that are explicitly there in the Adam space, or you can use the pattern miner to find patterns that appear in the Adam space when you apply a bit of reasoning at the point where you're trying to do the pattern match. And this is the sort of thing we want to be able to implement in sort of a slicker way in the future using a sort of an Atomies 2.0 language, because it has to do with how static pattern matching interoperates with these dynamic cognitive operations. And it's also like a simple type of cognitive synergy between pattern mining and inference. And then the other interesting intersection was to do with the evolutionary learning. So we have, Moses, which is a probabilistic evolutionary program learning algorithm, sort of associated with OpenCog, but right now it's been running outside of the atom space. When you use Moses to learn programs based on a certain fitness function, those programs can then be imported into the atom space for follow-on reasoning. But there's a project that's been going on for a while called Atom Space Moses to re-implement the atom space, to re-implement the Moses automated programming learning framework inside atom space entirely. And when that's done, then it can be used, among other things, together with pattern miner. So Moses it's doing evolutionary rather than non-greedy search. So you could use Moses as a control mechanism for pattern miner, which is not just doing the incremental greedy pattern mining that the pattern miner is doing, but is using evolutionary learning and probabilistic modeling of the evolving population to suggest new patterns. And I think that's probably ultimately what we need. Like the purely greedy pattern mining, which is done in the current pattern miner, that's great. I mean, it doesn't require any background knowledge or any special assumptions. You just go and find small combinations, slightly bigger combinations, and so forth. On the other hand, you'll never build up to really big and complex patterns that way, right? You'll get a bunch of simple patterns. Then evolutionary learning, if you have the right kind of structures in the atom space and or the right kind of prior knowledge, you could use that to discover much larger, more complex patterns, sometimes using the simpler patterns gotten through the greedy pattern mining process as inputs. So I think the current pattern miner can be quite useful right now in a whole bunch of different domains, just on its own, but sort of moving from narrow AI for pattern mining on graph and hypergraph knowledge stores toward AGI, the use of the pattern miner will be substantially about its integration with reasoning and evolutionary learning, which is all stuff Nil and I have been working on slowly in the background, whereas in this tutorial, the focus was on the stuff that already works quite well.
One of the things that inspired me a lot of this, recently was the open-ended evolution. So maybe that's like after you have this kind of greedy approach to finding things, maybe there is like some kind of approach which might explore and then pick some.
Well, there's one of the crazier ideas I had, which we haven't been able to explore yet, is in the 90s, I was really into an AI approach called algorithmic chemistry, which was developed by a guy named Walter Fontana. And there's related stuff being done now, like Marius Buliga's Chem Lambda system, which is quite cool. The idea there, you're getting beyond just simulate evolution to simulate chemistry. So you have like a little codelet acts on another codelet and produces another codelet, or maybe this codelet somehow catalyzes the combination of these codelets to produce a third codelet, right? And we were doing this in the 90s with little Lisp programs, actually, even as bad as computers were then. You can do much more interestingly with that now. Now that led to interesting theory stuff on, you can find like autocatalytic sets of programs and so forth, which all produce each other, which is quite evocative of biological systems, right? On the other hand, what I'd thought was, if you did this sort of algorithmic chemistry with codelets that live inside OpenCog atom space, then you can try to boost the evolution by doing pattern mining and reasoning. Find like, well, when I combine codelets of this type, it often gives me a codelet of that type, right? When the codelet of this type catalyzes this type of code reaction, that's often useful for this goal. So then you're using the pattern mining and associated reasoning in evolution to sort of accelerate the algorithmic chemical reactions. So that's my best thought about how to get like radical computational creativity going, right? Because I mean these sort of self-organizing autocatalytic evolving networks are how, at a certain level, that's how biology created all these weird forms like us, right? But then
life itself, life itself.
Yeah. Life Itself, which is a book by Robert Rosen, presenting similar ideas. Actually, yeah. The thing is, the current OpenCog framework would make that a bit awkward and inefficient. Although you could certainly do it. So we're sort of wanting to come up with a mathematically similar infrastructure that runs faster for playing around with these things. Although, to be fair, doing it in OpenCog now would be faster than what I did in the 90s, which still had some interesting results. But what you see, like what OpenAI is doing, largely they're taking algorithms that in concept have been known quite a long time, and they're just applying them on massive amounts of data and massive amounts of machines. So there's a lot of things you can do that with besides deep neural nets, like algorithmic chemistry as one example, or very many deep things in artificial life. We just don't know which of these things in artificial life or algorithmic chemistry didn't work because the scale was wrong, right?
Without compute, yeah. Yeah, I mean, it's interesting. One also interesting idea that I recently learned about is the idea about, I think that's coming from the neuroscience research. I think that the person is called, I guess you heard about him, Carl Friston, and he is basically talking about what makes something alive. What is this?
Well,
where is this barrier? What is outside of this thing, right?
I mean, so Carl Friston, he's a neuroscientist, and I can't comment on his neuroscience. I would say his attempt to formulate an entropy-based principle as the basis of intelligence seemed to have many holes in it, right? Because I mean, if you look at, I mean, he looks at minimizing entropy as the basis of perception, but when you look at what he's doing, pretty much he's just saying the model in the mind has to agree with the world. So it's really just minimizing KL divergence, which is not a new idea. And when I look at what he says about entropy minimization as a way to choose actions, he's sort of just saying that we need a model of what our actions will do that agrees with reality, which is just mapping action into perception. So I sort of felt like the philosophy is there, but the math isn't.
It's too simplified, maybe.
Quite there, yeah. So I mean that's what. I mean, that's part of what I was thinking when I was looking at, okay, if you have maximum entropy principles, then you have Jaynes with the maximum caliber principle, which is like maximum entropy for temporal systems, right? So you have it's like maximum path entropy. So if you have a system evolving from one point to another, given some observations of what the system did, what's the most probable hypothesis about how the system evolved? It's the one that maximizes the path entropy, the entropy of the possible paths the system could take, which is what he calls the caliber. Then you can look at like algorithmic caliber and just algorithmic information and see. So the notion of that given a bunch of observations of a system evolving over time, the most likely hypothesis for what the system is actually doing is that it's enacting the program with the maximum algorithmic caliber over that interval, and that ties in with like algorithmic Markov condition and like algorithmic Markov nets and so forth. So it seemed like there's a theory in the direction that Friston is pointing, but it's not the exact theory that he's pointing at. Now, from a neuroscience point of view, which is his background, who knows how much difference all these mathematical niceties make? I get a feeling they do make a difference if you really boil down to like quantum chemistry in the brain, which is where all the neuroscience magic is happening. There's probably some quantum information theory ultimately that you need there, for which it may actually make a difference to get the math of the information theory right. But we're not quite there yet. So all that's super interesting. On the other hand, I'm hoping I can set it aside to build AGI systems, right? Because that's
something more
that's all very hard on its own.
Right.
Yeah, there's that. I mean, how to measure information, which is what Friston is pointing at, though I don't like his answers. But how to measure information is certainly important for AGI also, right? Because the system needs to create intrinsic reward criteria for the things that it's learning, and like if for the patterns that it's recognizing. And this gets back to the pattern miner in a way, because you can use the pattern miner to look for frequent patterns, or you can use it to look for surprising patterns or interesting patterns. And there you have the question like, what is an interesting pattern, right? Is it one with a high like endpoint mutual information, like interaction information? Is it one with a high interaction information conditional on your knowledge? I mean, in a way, if you could solve the problem of correctly formulating what's an interesting pattern, that plus large-scale computing brings you a long way to creating an AGI, right? Like I thought this in automated theorem proving, for example, one of the shortcomings of the field is you don't have enough theorems to train your automated theorem prover. Like in natural language, you have a lot of sentences, but math, there's only that many proofs that have been formalized, and they're quite complex. So you want to train a machine learning algorithm on how to prove theorems by using existing proofs as examples. The number of existing proofs is arguably too small relative to the complexity of what the proofs are doing. So the solution will be to automatically generate a humongous number of new proofs. On the other hand, just randomly generating meaningless math theorems and then proving them with an automated theorem prover is probably not what you want to do. But if you could randomly generate billions of interesting theorems by the right interesting criterion, point your automated theorem prover at them, then you could generate a corpus of interesting math proofs like a billion times bigger than what we have now. Then you could train your machine learning theorem prover on it. And so and there's obvious recursions and virtuous cycles here, right? Because the better your theorem prover gets based on the machine learning learned from the corpus, the more easily you can prove more interesting theorems. But we don't yet have a really good formulation of what is an interesting math theorem, right? Because in some cases, one guy's interesting theorem is another guy's boring tautology. Like at one point in my life, I thought the quadratic formula was really interesting. I was like 7 years old or something, right? Or then like the generalized like Frobenius theorem that the only division algebras over the reals are real complex quaternion octonion. I'm still not sure if that's interesting or just trivial, right? So there's I mean, as a mathematician, that everything that's already understood is trivial and not interesting, right? So there's.
For me, I had sorry for interrupting, but regarding this interestingness, there is one project called Dreamcoder from MIT, Dreamcoder. basically they are trying to synthesize code, and their architecture comprised of two important stages, like baking and dreaming cycle. And basically, the dreaming cycle includes some of the neuro models like deep learning, and the baking cycle is more enumeration. But there is one possible criteria for interesting, basically subprograms, like subtheorems, like. And that's if you can refactor, for example, translated to domain of theorem proving or discovery in mathematics. If you can, for example, refactor some of your work in certain ways, so to use some kind of like a stepping stones. Maybe these are important theorems that then you can use to drive this process to find additional.
But it sort of recurses, right? You say an interesting theorem is one that's a lemma to a lot of interesting theorems.
Yes.
But it can't be the whole answer, though, right? Because where does the induction bottom out? Man?
Okay, but can you say? I mean, maybe it doesn't make sense. But for example, something which can simplify a lot of theorems, which might not be interesting in any way. Maybe that's valuable and interesting on its own.
Well, I think we're getting, the natural language terms here are a problem, right? Because interesting in this sense doesn't mean conceptually interesting. Like the commutative law of addition is not really very interesting, but it certainly is extremely useful, and it's a subcase of it's a lemma or whatever for a lot of different theorems. And I guess if you're in piano arithmetic, then getting the commutative law it is kind of interesting. It's a lot of S's you have to shuffle around to get to the commutative law, right? So that's what you said might be correct. I'm not.
It's compression.
It's not clear because the space of all random theorems is weird, and there might be some completely crappy. It might be that any theorem at all can be a lemma for a whole bunch of stupid random theorems that you don't care about. So it's you come up against like everything that we're interested in, or that any intelligence with any finite resources, intelligence in the real world could ever be interested in, is like in a teeny tiny little corner of the space of all possible mathematical structures, right? So like we're interested in things that can be composed hierarchically because our physics works that way and our brains work that way, but yet almost all proofs that you sample from random proof space have none of that, right? So
but if you have system which works pretty good for this completely chaotic something non-human relevant parts of mathematics, maybe it will be super easy then to just pick.
No, that may be sufficient, but it may not be necessary, and it may not be possible to find those things.
Okay.
But I mean, in reality, what you can do, you can build up a certain corpus of theorems, and you can see, like, if a certain lemma is useful for simplifying the proofs of a lot of them, then maybe it's good. And then that's sort of an interesting empirical / theoretical question, right? Because you could, like, we could look right now. I mean, we could take a whole bunch of genuine proofs, and then we could take proofs of theorems that humans care about, and we could generate like an equal number of true theorems that are just synthesized by like forward-chaining from axioms. Then you can pattern mine and see which patterns occur more often overall, or which patterns occur more often in the human math versus the random math. And then you would see, we could actually see which of these patterns were more useful as lemmas for proving more human math or more random math or whatever, right? So I mean, this it is actually tractable to experiment with now. One of the questions is, how similar are the answers for math theorem proving versus the answers to common sense reasoning? Because my son is doing his PhD in automated theorem proving, I've been talking a bunch to folks in the automated theorem proving community, and at an abstract level, they're wrestling with the same issues that Nil and I and Matt and so on are wrestling with PLN all the time. But the statistics of the theorem and proof space are different, right? Like in math, you have very few axioms and very long proofs. In common sense reasoning, you have very many axioms and very short proofs.
Short,
and it's
shallow proof.
yeah, so it's not quite clear which conclusions are generic across those two cases, and which conclusions are only good for math or only good for common sense. And then when you talk about a non-human AGI, maybe that dichotomy is less meaningful, and they're reasoning in some way that's like halfway between what we think of as math and what we think of as common sense. And it's not clear how fundamental that distinction is.
No, I think maybe the path towards separating or selecting is just create an AGI system, some kind of artificial system, which actually is doing autonomously physics research or any kind of science research, and it will basically try itself.
Yeah. I mean, that in biology, there are areas where you can do that now because they're in theory. I mean, there's automated lab equipment. Like you can do microbiology experiments purely with robotized lab equipment. So like an AI can crunch biology data, design a new experiment in the Petri dish, run it, take images, analyze the images, design new experiments. And this is not being done at large scale anywhere, but you certainly could. I think it would be really cool to do that in bubble chambers or something, because you would think the AGI might come with a whole different descriptive language for what's happening in the bubble chamber, because our words and our math for describing these things obviously are quite limited, and most events in a bubble chamber are thrown out as noise because they
What is bubble chamber?
Basically a chamber of gas that you're shooting elementary particles through to see the collisions of particles and the scatterings. And most events there are being thrown out as noise because they don't meet the criteria for an event of identifying a particle, right? But you wonder if you're pattern mining across all these events, like maybe there are actually interesting.
The noise, maybe this noise contains some information, but it's like
alien. Because there's quantum non-locality, and I mean there's quantum coherence in unexpected aspects there, right? So again, this is really big data, and we can't apply the OpenCog pattern miner to it in its current form. You can do something similar with different software, or we can wait until we have a massively faster OpenCog. But overall, setting aside AGI and OpenCog, there's no one even applying like the most advanced large-scale machine learning to like unsupervised pattern mining in data from particle accelerators and bubble chambers and so forth, because we're much more interested as a society in analyzing data on who will buy which useless garbage. So.
Crazy.
There's a question on YouTube whether pattern mining beats neural networks in terms of answering why did you do this. I'd say, I mean, neural networks is a very big field, but if we're looking at the types of neural networks in common use now, I would say neither pattern mining nor any of these commonly used neural networks is much good at assessing causality. But our PLN logic inference system, which is designed to work with pattern mining, has some causal inference built in. I mean, as such, as Nil presented it, the pattern miner is just looking at what patterns are there in the data without trying to disambiguate correlation from causation. In that way, it's similar to XGBoost or a neural network or whatever. But those patterns could be fed into an algorithm doing causal reasoning or an algorithm trying to extract causality from directed acyclic graphs or something. But so I would say pattern mining does better than current neural networks at generating raw materials to feed into a causal inference system, because it's very hard to extract information from within most current neural net architectures to feed into your causal inference engine. Whereas pattern miner, you can look at the details of what it extracted. It's transparent and explainable, which means you can feed it into a causal inference engine. Someone asked, Anatoly asked, can you hard code? Of course it could, but it would be even slower, right?
What's the question? Lambda link,
Question
URE?
was, could the hard-coded lambda link be implemented on top of the URE?
Well, maybe in principle, but in practice, the other way around.
Yeah. Oh no, Anatoly. That question is from Anatoly, who knows the system already. So, I mean, mathematically, you could do it that way. It would just be unnecessarily inefficient in the current implementation. I mean, there's no reason you couldn't.
Yeah, makes sense. Thank you.
Yeah, I mean, well, it depends on the other primitives, but yeah.
Well, I mean, yeah, sure. I mean, if you have basic predicate logic, you could build lambda in terms of a standard first order predicate logic or something. Right?
Yeah, I just noticed that in Prolog it's the other way around. So in Prolog they implement lambda calculus on top of pure
I mean,
logic.
Prolog sucks even worse than the current Atom space. So, and in many ways, I actually, yeah, this gets back to sort of Alexei's and my OpenCog 2.0 thinking, right? Like you really, I'm not sure you want either of those. You want logic or lambda. You want first order predicate logic or lambda calculus to be able to exist on the same atom space without having to shoehorn either one into the other one. But because either way is either Prolog way or the current atom space way is unacceptably slow for AGI, I think.
Yeah.
Ibby is asking if OpenCog can represent truth with a capital T.
Yeah,
Matt, do you have any comments on the absolute and eternal truth in OpenCog?
Can it represent Ben?
Well, yeah. I mean, well, I would say in seriousness, there's a lot of theories of truth out there in logic, right? And from a logic view, truth is about model theory, right? It's about setting up correspondences between your logic and your model. And what we're aiming for with scaled up OpenCog as we work on revising the system is actually a system that can concurrently easily represent multiple different logics and models and multiple mappings between them. So that's more like the postmodernist version of truth. We want various truth theories to be easy for the system to experiment with. But I mean, yeah, these philosophy questions we could interpret in a lot of different ways.
That brings up a whole. I mean,
yeah,
you
I mean,
have
the
truth.
Truth in formal logic has a certain flavor and history behind it, which doesn't capture all natural language interpretations of the concept of truth. Right?
Yeah, I mean, even like the most popular theory of induction, so Solomon induction. I mean, it is it's still arbitrary in a sense. We trust it because it works and it feels right. But I want to say, even when we're talking about truth as it relates to reality, it's just not clear what it is. So.
No, I mean, in practice, what we're thinking about is a system that can create models that are less erroneous than its previous models, right? And that's you are improving your understanding and reducing your stupidity. And I mean, like Charles Peirce, the philosopher, viewed that as something that was ultimately converging toward truth, even if you never actually get there. But we do, and a very nitty-gritty sense. I mean, in PLN logic, which is one of the key inference ingredients, probabilistic logic networks that we've been playing with in OpenCog, you label nodes and links representing terms or predicates with truth values, which can be single numbers or first or second order probability distributions. But we intentionally don't assume that you have a single consistent probability distribution over all the nodes and links in the atom space. And this is an important thing that PLN within OpenCog shares with Pei Wang's NARS, non-axiomatic reasoning system, which there's a tutorial on at this conference also. I mean, NARS doesn't use probabilistic semantics for the uncertain truth values in its knowledge graph, but NARS, with its non-probabilistic uncertain semantics, has in common with PLN that has its probabilistic uncertain semantics. I mean, it has in common, you don't try to have an overall consistent probability model over all your knowledge. And there's a couple reasons for that. One is, philosophically, we both sort of feel that's not how human minds work. And the other reason is it's quite inefficient every time you have a new bit coming into your system to have to update all of your knowledge based on that one bit of information. So as well as being conceptually questionable, having a consistent probability distribution over all your knowledge gets less and less efficient. And especially if you start to think about a distributed system or like a decentralized system implemented on something like SingularityNET, you just can't do all that updating, and that you get pushed toward what logicians would call a paraconsistent logic, where you can have some types of inconsistency, but that if a small inconsistency doesn't necessarily pollute the whole knowledge base and make everything inconsistent. And that's a sort of reason why we humans can think like, I love my girlfriend, I don't love my girlfriend, but we don't from this conclusion logically derive that like I will drown if I jump in the water, I won't drown if I jump in the water. Whereas a standard predicate or proposition logic system, if you have one contradiction, you can derive everything, right? Humans have some paraconsistent reasoning that isn't like that. What's interesting, as I mentioned in the previous tutorial or workshop rather, I think gradual typing on the programming language side is sort of as isomorphic to paraconsistent logic on the logic side. So if you create an atom space that supports multiple different type systems for different collections of nodes and links, and which lets you have nodes and links without their type specified initially, and then determines what type they have only when you need to for doing something with them, that sort of gradual typing system actually corresponds to a paraconsistent logical reasoning system, which I think probably is the right way to go for general intelligence. But again, that's a research hypothesis yet to be validated.
I have a question. there seems to be very good progress with PLN recently, and what I wonder is, what are your plans for causal inference in the future? Do you plan to integrate this component into PLN itself, or will this be a separate module or something like that?
So we're experimenting with causal inference now in the biology context for like trying to find out which, I mean, that's pretty simple. Like you want to cure a disease, you want to figure out which genetic variations, say, are actually causal for this drug curing someone of cancer or COVID, rather than just cofactors or correlation or something. So we're experimenting with that now within OpenCog, and it's, I mean, OpenCog acting on the outputs of machine learning algorithms along with biology background knowledge and so forth. And that's a case where there's, for many diseases and drugs, like there's ground truth knowledge about which things are causal and which ones aren't, that you can use to validate your methods. Like for cancers, there's some. For COVID or aging, there isn't as much. So I'd say at the moment we're in an exploratory phase with that. Like we had a bunch of math written down about causal inference in PLN, and we've been doing other causal inference stuff outside of OpenCog on biology data, just with information theory analysis. So now we're trying to see what will work in that domain, and based on what works or doesn't, we'll make a detailed path forward. But my guess is there's going to be a couple aspects to it. So I mean, one aspect is you have causal implication link in PLN, and then you can do inferences on causal implication link. So like A causes B, B causes C, in what cases and to what extent does A cause C, and so forth. And then you have interesting relations between intentional logic and causal logic, right? So there's interesting stuff there. On the other hand, there's probably also some sort of explicit search for DAGs that are causal DAGs embodying some approximation of an algorithmic Markov condition. And that may be like a DAG model structure search type thing, rather than a forward or backward chaining inference type thing. Like once you've done inference to learn a bunch of data, that data is all a tangled cross-connected graph with many, many links, right? So then in a way, it's like finding the maximum information partially spanning algorithmic Markov DAG, right? Like you're trying to find a causal model that summarizes this cross-connected graph, and maybe that's a separate process than forward or backward chaining, but of course they could both help each other. So that's because this gets back to pattern mining is greedy, right? And in a sense, forward and backward chaining inference are greedy also. They're going step by step, although we can try to guide them with machine learning models, trying to have prior proofs, which are a little less greedy. But you could, for example, use evolutionary learning to try to evolve causal DAGs, right? And then that's not greedy in the same sense, because you're crossing over one okay causal DAG with another okay causal DAG to find a maybe better one, like in the genetic operator sense. And you can build a probabilistic model of the structure of the causal DAGs, like in Bayesian optimization algorithm applied to program evolution, right? Where you say, we have these okay causal DAGs, these bad ones. So what's a probabilistic model of the structure of the good causal DAGs versus the bad causal DAGs? And then that's like basically atom space Moses used to evolve causal DAGs, where the fitness of a causal DAG has to be figured out by PLN inference against the atom space. And I mean, ultimately, I think that's where we have to go. I hope we don't have to go there to solve the bioinformatics problems that we're we're facing right now, because that the ultimate thing I just described is quite difficult, right? I mean, how are you doing causal inference in NARS now, actually?
Oh, currently it's a quite simple approach where we essentially apply subcoding. So we just have a implication relationship, which might be similar to what you use. And from there, so when a core enters the system, it simply tries to infer a subcore, and the subcore will then enter something we call attention buffer, a cycling events queue, and the subcore usually has will then, for instance, be processed next, and then the process repeats until it at some point might come to a point where the precondition of implication is already satisfied, but there is something like a operation attached to the link. So at this point, it can then invoke a behavior to get the next step, essentially. So to reach a certain subcore. So it's essentially it tries to search in all kind of directions via inference, and some of those directions can then meet with current circumstances, and whenever this is the case, it can invoke an operation in order to reach the next subcore. This is how it's currently handled. So it's a quite simple process, but more tricky, as you mentioned. It would be great if it could do some kind of hierarchical planning, or to be able to handle a hierarchical structure. It's not yet quite clear how to do this the best way. And so far it works especially well if there are just some change from subcores to a certain core the system wants to reach. This works pretty well, but ideally it would be able to handle some cases like traditionally handled by hierarchical planning, but there's still a lot of work to do.
Yeah, I mean, that's, I guess, learning hierarchical plans, if you have enough data presented in the properly staged way, should be possible, right? I mean, but that's, thinking about it in a NARS context is interesting, though, because all my thinking about causality in the last 10 years has been sort of information theory, which is pretty much probability theory with logarithms, right? And then the connection between information theory and algorithmic information theory. And then in NARS, since it's not probabilistic, the information theory and algorithmic information theory models of causality don't directly pertain, but the basic sort of grounding of causality in action pertains, right? So it's still like a, you know, if me throwing this coffee cup causes it to break, you still have the grounding in this do relation, that this action implies the result. So it's kind of an interesting exercise to think about what aspects of causation can be abstracted and aren't tied to specifics of information and probability. I had not thought about that much. But the hierarchical planning part should be fine, right? Cool.
Especially it seems to be difficult to make sure the system forms the right categories. For instance, because when we plan ahead, for instance, to go to the airport to fly to another country, we don't plan every motor action, right? We only plan we say something like, at first we have to leave the house, then we take the train to the airport, and so we have quite a high level representation of which actually to be executed only then when we think about it. step, only then we begin to think about the details.
But do you think that's qualitatively different than learning abstraction hierarchies of concepts in domains other than planning, or is it basically the same problem?
I hope it's the same.
Yeah, right.
Maybe the key about hierarchical planning is just to build a confidence about the planning itself and about the capacity to fill the blanks. And then once you have this confidence, then you can say, okay, well, I plan this, and then I'll figure out and I'll figure out what's in between, and I know I can figure it out. And then normally you should be able just to to have a formal proof. I mean, a formal proof of an estimate that say, well, yeah, you're gonna solve the goal because you have that confidence how you're gonna be able to.
It just feels to me like when a human is doing a travel plan or something, we come to that with a very rich abstraction hierarchy of relevant concepts already. It's not like we're not usually learning those concepts in the context of forming the plan. We have those concepts in our head already, and so then we naturally use them in forming a plan. I guess in some cases, I mean, if you're learning to play a totally new video game from scratch, then you may be forming the concepts why you plan how to win, and there's some more sort of equally weighted feedback between those two processes. But that seems harder than most of the planning we do in everyday life. It seems like mostly we have the abstraction hierarchy already.
Great, that's a good point.
But maybe it's not true for like a 6-month-old baby, right? I mean, I think it's true. It's true for me now, but I'm mostly operating in environments I've been operating with for decades, right? If you look at a little kid that's planning how to build something with a new set of blocks or something, I guess they're trying to build that tower. And as they try to build that tower, they're learning the properties of the blocks they're building the tower with. And so that I guess that they're in that preschool setting, you do sort of have that feedback between planning and then concept formation from the objects. And that, I think, of course, that's why we designed that environment to have very simple goals and very easily categorized objects. And it still takes these brains like months or years to solve this coordinated problem of planning and concept formation. But yeah, this sort of ties in. Nil and I and some others in the OpenCog are just starting to get back into this sort of toy Minecraft-like domain for learning. Because I mean, we've been working on all sorts of other stuff, but it seemed like now we're facing some questions where it would be cool to try some really simple domain, just to do some exploratory work. And yeah, building stuff in a Minecraft-like domain that seems to be a case where the plans and the concept formation may be co-learned. But it's interesting that it's hard to come up with good examples for that in everyday adult life, actually, because I guess, see, as adults we can learn very big, complex hierarchical plans. Little kids tend not to do that. So I mean, seems like when the concept learning and the planning are like co-evolving, you're looking at pretty simple plans, and it's only the really large, well fleshed out hierarchical ontology that lets us come up with the fiendishly complex plans that
yeah, we're coming back to the difference between common sense reasoning and mathematical reasoning, where, well, common sense reasoning, there's no point going beyond a few steps because the uncertainty.
Yeah, but there's other things like you're looking at like business strategy or planning a military campaign. These are not quite common sense and they're not quite mathematical, but they are they require quite complex planning beyond what a preschool kid can do, right? And then maybe they do use common sense reasoning in the sense of uncertain reasoning, like PLN is doing. But we also tend to use written aids for these as humans, right? Like they go beyond our working memory in some sense. Planning a complex software project is the same thing. It's not math, but it's not common sense either. More questions from YouTube. Here's a question. Can we build progressive lattice of instantiated causal knowledge upon which to project perceptual understanding of impact, in which over time aspects can be instantiated as extensions? Yes. All right, that's easy.
How long is the better question?
Yeah. When it will be delivered is another problem.
But yes, we can.
I think
Conceptually.
That's sort of just what was coming out in the discussion with Patrick, like that lattice, that hierarchy of instantiated causal knowledge is part of your ontology of the world, which is how you can make these high level plans.
So should we set
the role of scale is interesting to think about here, right? Because we've seen things like, multi-layer perceptrons for image processing didn't work too well in the 90s. Now they work extremely well. And a lot of this is the scale allowed you to tune and fiddle with the algorithms to get them to work very well by making it so much faster to run experiments. As well as making it faster to run the trained models. So that the experiment of running like common sense logic engines for causal reasoning on the scale of like what OpenAI is doing with neural nets. That hasn't been done yet, right? And so it is by doing so, some things that seem to be conceptual problems now may turn out to not be problems at all and just be problems of inadequate data, because to build this deep concept hierarchy just requires a large amount of rich information to feed in. Causation is very sort of impure concept, at least causation as humans understand it conceptually. And I guess we come to it from a whole lot of experience with trying to manipulate physical objects and humans and groups of humans through our childhood. And we haven't yet seen what an AI can do when fed with that kind of data.
I personally think it's
hopefully in the next few years, right? Now we're kind of poised for it. So.
I think it's more complex than just throwing more hardware at it, though. I think it's like you were talking.
It is
the algorithms with the hardware.
Yeah, but if you take the deep neural net analogy, like the exact multi-layer perceptrons I was teaching in the 90s with recurrent backpropagation, like still don't do very much, right?
Right.
Exactly. On the other hand, having faster computers made it much easier to figure out which variation on that architecture worked well. And like transformer networks, which we're using for our applied work on natural language processing now, and also trying to hybridize with symbolic grammar learning in a paper that Andres Suarez is giving in this conference for unsupervised grammar induction. I mean, these are certainly different than neural nets from 10 years ago, but they're also not that different, right? I mean, all the ingredients were there. It's just no one was smart enough to figure out how to combine them purely with pencil and paper, right? Like you figured out how to combine them by being able to fairly rapidly experiment with variations on the architecture. And I think that cycle hasn't happened with symbolic, like uncertain logic for causal reasoning yet, right? There's been a lot of nice math written down and experiments done on toy problems, and experiments with extremely simplified versions on large data sets. And the more fully fleshed out theories we've never been able to experiment with them in large data sets. So I mean, I certainly, once we can, we're going to figure out many particular things we think are smart now are actually stupid, and make many changes to specific formulas and axioms and so forth. The cool thing is we should soon be in the domain where you can fiddle around with your truth value formulas or the axioms of your logic and see what implications it has for a system doing causal reasoning on like a huge, on a realistic body of knowledge, which is by soon I mean within a few years. I don't think we're there quite yet, because we don't have the scalable implementation of any of these. I mean, we don't have an implementation that allows large scale, rapid experimentation with the suitably complex versions of these AI tools we're talking about here. We could run pattern mining on a huge distributed atom space if we want to, but we're going to see constraints in how we configure it, so that to get it to work scalably on a huge atom space, you'll have to restrict what sorts of patterns you're looking for and how the search is proceeding. And I think these restrictions will gradually get lifted over the next few years, so we can really let these algorithms operate in more generality on real world data sets. I mean, as an example, letting pattern mining run where it's doing a little inference to check whether a certain sub-atom space matches the pattern. Like right now, that just slows things down so much. You can only do it on small problems. If you want a large problem, you can't be folding the inference through the pattern mining like that.
So maybe some kind of a compilation approach, or just-in-time compilation approach might scale things up. I mean, maybe some kind of a setup where a system which enough these building blocks, logical and probabilistic building blocks, is looking at how things are being executed on a CPU or GPU, and then automatically is trying to create these implementations, very specialized implementations, which might speed up or speed up computation, which is required to get some inference or conclusions, and then create maybe automatically, maybe with some kind of human guidance, the next layer of the.
You know, I was friends in the late 90s and early aughts with Valentin Turchin, who was sort of the founder of Russian AI in the 60s. He lived in New York then, and he invented supercompilation in the 1960s and 70s. So his way to make human level AGI, in essence, it was like take AXE, although he didn't call it that, he had the idea, take AXE and program specialize it to the human body, and then you're done, right? So, yeah. But there was a problem of scaling up the program specializer, right? So So yeah, I think yes, certainly there has to be the ability for the system to automatically specialize its cognitive operations, for example, inference control heuristics to the specific problems that it's looking at. And I think I mean that requires a pretty advanced cognitive system, but it has to be there. Like I think like one, you know, you remember if you studied inorganic then organic chemistry, you have to tweak your inference control mechanism to deal with organic chemistry because the molecules are so big and there's so much there. Or in a preschool context, when kids go from like Duplo blocks, which are big Lego blocks, to the smaller Lego blocks, you know, you have some transfer learning, but you also have some change of the inference control heuristic, like the way they're reasoning about what to build is different with the little blocks because they stick together better. They stick together better, so you can build bigger and more complex things. But that then you get hierarchical plans, which you can't ever get to with the smaller blocks, right? And you then because you have these hierarchical plans, then you need different inference control heuristics. So I think yeah, you need. I mean, this was one of Nil's and my ideas for a while. Pattern mining is like the base case for learning inference control heuristics. So you do a lot of inference. You do pattern mining on the saved inference DAGs. Then using those patterns that you mined, that forms a distribution over which inference paths are good. But that's the base case of the recursion. Then the next case is using inference to infer about which patterns in inference trees are useful in which contexts. But the context dependence is the crazy part, right? Because the inference control heuristic for inferring things about similarity between people may be different than the inference control heuristics for inferring about, say, logistical planning or something, right? But then you can explicitly represent the context dependence of an inference control heuristic in the atom space, and then that context dependence is part of the data fed into the inference engine. And the human brain obviously does all this in its own way with a less explicit knowledge representation, right? All right, yeah, we have some lighter weight questions here, or so heavyweight they have to be treated as lightweight. Like one, OpenCog seems to be about intelligence. Is there any work on sentience? Is that necessary or sufficient for the other? So, I mean, intelligence, we have some formal definitions of, which you may or may not accept, but at least they're there. Sentience is a lot vaguer, right? So, I mean, if you're thinking about sort of practical, reflective consciousness like humans have, where we have a working memory and a knowledge of ourself and others and so forth. I mean, this I think would come from using a system like the one we're building in OpenCog to control, you know, an autonomous agent moving around in a physical environment and communicating with other similar agents in a shared environment. So I think the structures of self and others and the illusions of free will and identity and all these things that make our inner lives what they are, in a structural and dynamic sense, I think those would come out of putting this kind of learning algorithm to do the kind of task that humans do. I mean, then you have the whole qualia problem of like, would this thing feel like people do, which is a whole other philosophy problem that I don't want to try to answer here, although I've written a lot about it in the past. I mean, I tend to be panpsychist and think everything in the universe is conscious. And so if the structures and dynamics in this digital system are vaguely like those in a human, then maybe its subjective experience will be vaguely like those in a human. But that's a whole other deep philosophical story. And I guess most of our thinking in OpenCog project is you can build something that appears to think like a human or even smarter than a human without necessarily fully solving that philosophy problem of the nature of experience, which we haven't solved in the human domain either. All right, I seem to have accidentally taken over this Q&A session due to having a bigger mouth than everybody else. But maybe someone else has something to say now.
Who will dare? Let's see.
Well, there was another question. Could we use a biological approach to build increasingly complex capabilities of organisms by using causal relationships between concepts? I don't know what a biological approach means in this context. I think both in like evolutionary algorithms and in algorithmic chemistry, as I mentioned, you're certainly being inspired by biology. And for the algorithmic chemistry concept I mentioned, there was a blog post I had 4 or 5 years ago, which I called cogistry, very ugly word, which I hope doesn't catch on. But anyways, cogistry, like cognitive chemistry. I tried to explain this soup of intercreating codelets with inference and probabilistic reasoning and pattern mining to accelerate its evolution. But I mean, these are very loosely biologically inspired. And I guess if you really get deep into biology and artificial life, it's cool, but it brings you in a whole different direction, right? Because I mean, the reason biology is as generative as it is, generating so many different cool things that actually work, comes down to chemistry. And then the reason chemistry works is physics. And then it's like either you have the periodic table of elements and molecular orbitals and all that, or you try to understand what are the principles that make the periodic table work as nicely as it does, which is very, very cool. However, and that may be a way to make AGI, but that's a whole other direction to take, right? So I think when you think deeply about AGI, eventually you realize like human-like minds are a very tiny corner of the subspace of all possible generally intelligent minds. And there's probably a host of different ways to even implement human-like minds, let alone other types of minds. So the challenge we have is to find a way that will work tractably, right? And once you have that, then that either by its own thinking or as a tool to help your research, that first mind can help you explore all the other avenues, which is it's probably a good note to end this long, rambling, and hopefully entertaining Q&A session on. So yeah, thanks everyone for attending the tutorial and the follow-on wide-ranging discussion. And yeah, thanks to Nil and Matt and everyone from the OpenCog side for leading things. So